Hi guys, we're going to get started today. This is the video for section 9.3 part A. It's the second to last section before we finish our very first unit. And we're going to be talking about relations and functions. We're still going to be doing it in terms of set theory, which is that sort of big broad umbrella that gives us a big picture view of things that we normally do all the time, but it will help us to sort of understand it from all these different angles that we're not used to looking at it, in the hopes that it makes us better able to understand when our students get tripped up with some of these concepts when we're educating them in our classrooms. All right, let's get started. I'm going to start sharing my screen now. All right, I think you can see that here. Move it over a little bit. I'm going to try to minimize this here so it's not disturbing our view. There we go. Okay. So as you can see, and apologies for it being slightly blurry, I'm not really sure why that is. Today we're going to start talking about relations and functions. And these are two different things, although they are related to each other. No pun intended there, okay? A relation, we use that, and you can see here, we use a relation to represent a relationship between two numbers or objects. So you've actually been using relations all the time. Here are some basic simple examples that you have actually probably seen. For example, when you say -3 is less than 7, that's a relation, okay? If you say that 2 is a factor of 6, that's also a relation. Think relationship. We're basically stating that there is a relationship between these two numbers, and that relationship is what we're stating. We're stating that 2 is a factor of 3, okay? Here we're stating the relationship that triangle ABC is similar to triangle DEF. That's a relation that we might discuss in a class of geometry. Now, let's talk about the official definition. Okay, this is the official mathematical definition of what a relation is. Don't get too caught up in the language. We're going to talk about it step by step. Okay, so officially, a relation, and we normally call that R, that's the notation that we use. Okay, relation R comes from a set A to set B. Okay, it comes from them where we take their Cartesian product. Remember the cross right here? It's called the Cartesian product. So relation R from set A to set B is a subset. So will always be, and this is important, it is a subset of the cross product. Okay? So, and then if, this is the next thing you have to remember, if it turns out that set A and set B were equal to each other to begin with, before we took their cross product and then found the subset of that cross product that fit the relation we were talking about, then when set A and set B started out being equal to each other to begin with, we say that the relation is in relation to set A. But that last part, not the most important part for you to remember. So now let's walk through this definition looking at this example. Okay? So here we have set A. Here we have set B. Okay? Set A contains 2, 4, 6, and 8. Set B contains 2, 4, 6, and 8. So right away, we know that it's already fulfilling this last part right here because set A is indeed equal to set B. Remember that in set theory, the definition of two sets that are equal is that they contain the exact same elements as well as having one-to-one correspondence. And these two sets, set A and set B, do indeed have the exact same elements, as you can see here, and obviously they also have one-to-one correspondence. So we can say that these two sets are equal. This is only important for us to note because it fulfills this last part of the definition. Okay, so obviously whatever relation we come up with, is going to be a relation to set A because they are both equal to begin with. Okay? Now, to create our relation, we must first take the cross product or the Cartesian product of these two sets. So that's what we're doing here in this very first part, okay? Here is the Cartesian product that we're going to take from the two sets. That, if you remember from when we introduced this, that means that we're going to create ordered pairs, right? So we create these ordered pairs by saying, all right, well, 2 goes to 2, there it is. Then 2 goes to 4, right? There it is. Then 2 goes to 6, and then 2 goes to 8, and we have those right here, okay? And then now we begin to do that with the 4. So 4 is also going to go to the 2, and 4 is also going to go to the 4, and it's going to go to the 6, and it's going to go to the 8, okay? I'm not sure why the 4 to the 2 was missing. Well, the reason why we didn't write it down for 2 is because these two are in essence the same, right? Remember that in set theory, order inside the pair doesn't matter. The elements are still the same. If just because you flip the order doesn't mean the element has changed. So this is 2 goes to 4 or 4 goes to 2. They're the same. All right? So then we have, here's the 6, it's going to go to the 2, to the 4, to the 6, to the 8, and you see that there, right? Okay, so we do the Cartesian product, and now out of this product, okay, and this is right here, just for efficiency's sake, you'll see that I did not do the exhaustive Cartesian product, but you could have done that yourself, okay? 8 goes to the 2, to the 4, to the 6, to the 8. Okay, you can see it there with all my arrows, the exhaustive Cartesian product. Now, out of this, so out of the Cartesian product, we are now going to take our relation, okay? And in this case, we're going to say that our relation is going to be called is a factor of. In other words, that's what's going to determine which one of these cross products we're going to pull out to put into this new set called the relation. That's why the definition says that R is always a subset, okay? Because once we take the Cartesian product, R, depending on what we call it, in this case it is a factor of, so those are the parameters that we have set for it, gets pulled out of that Cartesian product, okay? So we're going to say that R is a factor of, so the only ordered pairs that we're interested in from the Cartesian product are the ones where we can read it left to right as this one is a factor of this one. So if we look there, we say, okay, well, 2 is a factor of 2. Yes, it is. So that comes into the relation, okay? 2 is a factor of 4. Yes, it is. So that pair makes it into our relation. We go back up here. 2 is a factor of 6. Yes, it is. So that makes it into our relation. Then we go over here. 2 is a factor of 8. Yes, it is. So that makes it into our relation, okay? Now, here's one of the reasons why the 4, 2, this right here, doesn't make it into our relation, because is 4 a factor of 2? No, it's not. So it does not make it into our relationship. But is 4 a factor of 4? Yes, it is. So it makes it into our relation, okay? Is 4 a factor of 6? Now we're looking over here. No, it's not. So that's why it doesn't make it into our relation. But is 4 a factor of 8? Yes, it is. So it makes it into our relation. Okay? So you keep doing that until in the end you realize that out of the cross product, the only ones that make it into the relationship are right here, because they fulfill the parameters of that relation, which is that they is a factor of. Now, because now we've created our subset, right? R is indeed a subset of the Cartesian cross product of our original set A and set B. And because in the beginning we knew that set A and set B were equal to each other, we can also state the last part of the definition, which is that R is a subset of the Cartesian cross product of set A and set B, and it is a relation to set A. Why? Because set A and set B were equal to each other. And therefore, here we fulfill all the points of the original definition of what a relation is. Okay? I'm hoping that's not too complicated. That's why I'm glad that I'm videotaping this for you, because you can go back and sort of listen to it again and walk your way through it. So that is how we create a relation, okay, in set theory. Now, there are some properties that relations have, okay? And that's what we're going to talk about now. So let's talk about some properties that the relation has. Okay? Let me see here. So the first property that a relation can have, okay, now these are not a must. In other words, we've already defined what it takes to be a relation. These properties exist in some and not in others. So it's not a must, but it is something that occurs, all right? So a relation can have what's called the reflexive property, okay? The reflexive property is defined as every element in set A is related to itself. Because remember, we're saying that if the two sets that we originally take the cross product of are the same, it's kind of like saying that we're talking about only one set, right? So if the relation that we're talking about is a factor of, and here's set A, what you have to think about is that you took set A, okay, which had 2, 4, 6, and 8, and you did the Cartesian cross product with itself, 2, 4, 6, and 8. Okay? And that those are then, you take that cross product, and out of that cross product, out of that new set that gets created by that cross product, you're going to pick the ones that fit into our relation is a factor of. Okay? Well, if you look at it, 2 is a factor of itself. Yes, it is. So that's reflexive. Is 4 a factor of itself? Sure is. Is 6 a factor of itself? Sure is. Is 8? Yes. Look at what happens if we take the actual cross product, okay? The cross product would be, here's the new set that we're creating, 2, 2, there it is, there's the reflexive, okay? Then it would be 2, 4, 2, 6, 2, 8, okay? Then we'd go 4, 2, which you don't really have to write down. Then we have 4, 4, there's the reflexive. We have 4, 6, and 4, 8. Oh, sorry, that 8 is kind of nasty. Let me see if I can fix that for you. That's a little better, okay? And there's the comma. All right. Then we have 6, right? So then we'd have 6, 2, 6, 4, 6, 6, and 6, 8. And then you have 8. We're at the bottom now, so we have 8, 2, 8, 4, 8, 6, and 8, 8. Okay? And as you can see, in that cross product, if we're looking for the property, is it reflexive? It sure is, because in that cross product, we have the following. We have 2, 2. We have 4, 4. We have 6, 6. We have 8, 8. Now, to be sure that the relation is reflexive, the relation says that it has to be a factor of, right? Well, if we look at these, is 2 a factor of 2? Yes, it is. Is 4 a factor of 4? Yes, it is. Is 6 a factor of 6? Yes, it is. Is 8 a factor of 8? Yes, it is. So those 3 pairs that we found when we took the cross product of set A with itself, okay, exist, number 1, and number 2, fulfill the parameters of the relationship that we said is a factor of. So because of that, we can say that the definition of a reflexive property is that every element in set A is related to itself through that relationship. That's why we only worry about set A. Okay, hopefully that helps to make it clear. So therefore, we can state with confidence that R is a reflexive relationship, and it contains that property. Okay? I'm going to go ahead and get rid of the work we did here on the side, so this is a little more readable. There we go. And let's continue. Now we're moving on to the next property. The next property is whether or not it's symmetric. And it's defined as if one of the pairs from the cross product is A comma B, and that happens to be an element in the relationship. And then it turns out that the other pair, B comma A, is also an element in the relationship. Okay? So the relationship we're going to look at for our example is that R is the opposite of. Okay? And here's the set A that we're talking about. So once again, if we take the cross product, because remember, the relation is a subset of that cross product. So we have to take that Cartesian cross product first, and then out of that, we pick out the elements that belong in this relation, okay? So if we do that, and we have set A, I think this time for visual sake, we're going to do it this way. We've got 1, -1, 2, -2, right? There's set A. And now set B would be set A again, because we're taking the cross product between itself, right? So remember, because we said that A is equal to B. So we're going to say 1, -1, 2, -2, right? And we're going to go ahead and take the Cartesian cross product of that. We have 1 goes to 1, 1 goes to -1, 1 goes to 2, 1 goes to -2, right? Then we have -1 goes to 1, -1 goes to -1, -1 goes to 2, -1 goes to -2, okay? Then we have 2 goes to 1, 2 goes to -1, 2 goes to 2, and 2 goes to -2. And lastly, we have -2 goes to 1, -2 goes to -1, -2 goes to 2, and -2 goes to -2. Okay? Now, that is the entirety of the cross product. The ones we're looking for, though, is the opposite of. So I'm going to start at looking at the red ones. 1, 1, not the opposite of, so I'm not putting that into my relation. But 1, -1 is, so there it is. Okay? I'm sorry, let's do that again. Here's 1, -1, okay? 1, -1. Then 1, 2, they're not opposites, so I'm not going to include that, okay? And 1, -2, also not opposites, so I'm not going to include that. So that's it for the red, okay? Now I'm going to look at the yellow. -1, 1, they are opposites, so I am going to keep that one. -1, 1, there it is, okay? -1, -1, they're the same, not opposite. -1, 2, not opposite. -1, -2, not opposite, so I'm not including that. Now let's go to the blue. 2, 1, nope. 2, -1, nope. 2, 2, nope. But 2, -2, yes, so there it is. Okay, 2, -2. And now I'm going to go on to the pink. -2, 1, no. -2, -1, no. -2, +2, no. -2, I'm sorry, yes, -2, +2, absolutely. See, there it is, -2, +2, okay? And those are the ones that fulfill the relation is the opposite of, So here they are. Here's the subset from this cross product, right? And there it is, we took that cross product. Here's the subset of it, and these are the elements that fulfill the parameters of the relation. Now, the definition is it symmetric? And that means, do we have A, the element AB, is also in the relationship as the element BA? Well, let's see, okay? And I'm going to use a highlighter for that. Here we have 1, -1. In this case, we could name this A and this B. Do I have another place where I have these same elements but switched? Sure do, right over here. The yellow one also has that, but in this case we have B, A. So they are the opposite of each other. And both of them are inside the relation. Now let's look over here, all right? We've got 2, -2. If we call this A and this B. Do we have somewhere where the A and B are flipped? We sure do, right over here, where we have B and then A. So sure enough, they are reflexive. So because we have this element right here that is also showing up in this relationship but in opposite order, and we have this element right here which is also showing up in the relationship but in opposite order, this relation is reflexive. Okay, and I'm sorry, this relation would then be called symmetric, not reflexive. Reflexive means that the relationship goes in and on into itself. Symmetric means that we have the flip-flop happening here, the AB to the BA, the AB to the BA. Okay, so therefore this relation would be termed as a reflexive relation. The relation again that we're talking about is this one right here, is the opposite of. This relationship is indeed reflexive. Okay? All right, let's get rid of this and move on to the next property we want to talk about, which is transitive. All right? Now let's look and see how a relation can be transitive. It is defined as if element AB, right, is an element of the relationship we're talking about. And then we also have an element situation where B comma C is an element of the relationship we're talking about. And then it turns out that we also have an element called A comma C, okay? Then this is considered a transitive property. Let's look at it in an actual set so that it makes a little bit more sense, okay? So if the relationship we want to talk about is this, that R is a factor of, that's the relationship we're looking at. Here's the set we're talking about, okay? Again, we're going to take the cross product of the set first. And because we're doing it, because A is equal to B, it's really a relationship of A, which is why we're only looking at set A. But let's do it again like we did before. So we've got set A, and we'll use the red. Go ahead. We have 2, 4, 6, 8, 12. Okay, so there's our first set. And then we have our second set, 2, 4, 6, 8, and 12. Okay, here's our second set. Let's take the Cartesian cross product of that. Okay, so we start with 2 goes to 2, 2 goes to 4, 2 goes to 6, 2 goes to 8, 2 goes to 12. That is our first set of pairs. Okay, you can see them here. Here's 2, 4, 2, 6, 2, 8, 2, 12. Okay, then we move on to the next one. We'll do that in pink, and it goes 4 goes to 2, 4 goes to 4, 4 goes to 6, 4 goes to 8, 4 goes to 12. Okay, then we'll do it in green. 6 goes to 2, 6 goes to 4, 6 goes to 6, 6 goes to 8, 6 goes to 12. Then we'll do it in yellow. 8 goes to 2, 8 goes to 4, 8 goes to 6, 8 goes to 8, 8 goes to 12. All right, and last but not least, we'll do it in blue. Oh no, we used blue already. Let's I guess we'll have to do red. Hopefully that's not too confusing. We're gonna do 12. And 12 goes to 2, 12 goes to 4, 12 goes to 6, 12 goes to 8, 12 goes to 12. So there is the whole cross product, right? Now, out of all those cross products, the ones we want in our relation is a factor of. So let's start with the blue ones. 2 is a factor of 2? Yes. Okay? So we're going to have it here. And I'm not sure why it's not listed, but we'll do it. 2 is a factor of 2. Yes. Is 2 a factor of 4? Yes. Is 2 a factor of 6? Yes. You can see that it's there. Okay. 2 a factor of 6? Yes. 2 a factor of 8? Yes. So it's there. Is 2 a factor of 12? Yes. So that's in our relationship. Now let's move on to the pink. Okay. We start with 4. Is 4 a factor of 2? No, so that's why we don't include it. But is 4 a factor of 4? Yes, it is. So there it is. Is 4 a factor of 6? No, so not included. Is 4 a factor of 8? Yes, so there it is. We include that in our relation. Is 4 a factor of 12? Yes, it is. So we include that in our relation. Okay? Now let's go on to the green cross products. Is 6 a factor of 2? No, it's not. So we're not including it. Is 6 a factor of 4? No. Is 6 a factor of 6? Yes. So we include that in our relation. Is 6 a factor of 8? No. But is 6 a factor of 12? Yes. So we include that. Okay? And now let's go to the red ones, which were our 12. Yellow, which was 8. Is 8 a factor of 2? No, so it's not included. Is 8 a factor of 4? No. Is 8 a factor of 6? No. But is 8 a factor of 8? Yes, so we include it. Is 8 a factor of 12? No, so not included. And now we go to the red ones, right? Is 12 a factor of 2? No. 12 a factor of 4? No. 12 a factor of 6? No. 12 a factor of 8? No. 12 a factor of 12? Yes, so we're going to include that. 12, 12. Okay? And this is our relation. Okay? Our relation, where all the elements in here fulfill the idea that is a factor of. Now, we're looking to see if it's transitive, which means we're looking to see if we start with an element that has A to B, then B to C, and A to C. Let's see if we do, okay? We're going to go see. Let's say we call this A and this B, all right? And we're going to highlight it green. 2 to 4. Do we have somewhere where 4 goes to something else? Yes, we do. We've got somewhere right here where 4 goes to 8. So there's A. There's B, okay? But it's going to another number, C. C is 8. So do we have somewhere where 8 goes back to A? A was 2, right? So do we have somewhere where 8 goes back to 2? Yes, we do, right here. Okay? Where we have A and we have C. So because we have those three, these three right here, this is transitive. Let's see if we can see it again, okay? Because it's there again. For example, we have, let's do the one for 6, okay? We'll do it in pink. Here is 2 goes to 6. So 2 will be our A, 6 will be our B. Okay, so now we're looking for 6 going to something else. All right, we have 6 going over here to 12. Okay, so there's our B. Let me go back. There we go. There's our B, and our C is 12. Now, do we have a A, which was 2, going to 12? Sure we do, right over here. So here's A again, which was 2, but this time it's going to the C, which was 12. So it is transitive. It goes from here to here to here. It is transitive. Okay, that's the transitive property. So because of that, okay, we can say that the relationship is a factor of, and I'm going to try to highlight it here. Oops, sorry. There we go. Is transitive, okay? And we've just shown how it is. Now they want you to note, and you can see it here as well in this notation where they have it here. Here you have A, B, 2 to 4. Here you have B going to C, 4 to 8, and then you have A going to C, 2 to 8, okay? Which is the one that we looked at first. So there's your example there. And now we know that it is transitive. Okay? Now, I told you that any relation that we look at could have one of these properties, might not have one of these properties. However, when you get the trifecta where it has all 3 of the properties, we call that an equivalence relation. Okay? And that's how it's defined. It is a relation that is reflexive and symmetric and transitive. So it checks off all of the 3 properties that we've talked about. When that happens, then that relation is called an equivalence relation. When that does not happen, it's just a relation that has the property of being reflexive, or it has the property of being symmetric, or it has the property of being transitive. But when it has all 3 properties, it's the trifecta, and then we call it an equivalence relation. Okay? Let's look at an example of an equivalence relation. So here's our example, okay? The relation we're looking at is same ones digit as, okay? Now, this time I'm not going to take the cross product for you on the side before we pull out the elements from that cross product that do fit into the relation, because as you're going to see, it's a very large set, so we would take up a lot of space. But the set we're looking at is right here, set A, that contains all the digits from 1 to 40, okay? All the numbers, rather, from 1 to 40. And the relation we're looking at is if we did the cross product of set A to itself, we're looking for the grouping of the numbers that would have the same ones digit. And here you see some examples of that, okay, that would fulfill that relation. We'd have 1 goes to 1, right, and they would have obviously the same ones digit. 1 and 11 would have the same ones digit, 1 and 21, 1 and 31, and then that's where it would stop because we're stopping at 40, so we don't go to 41, right? And then if we go to 2, same thing. You got 2, 2, 2, 12, 2, 22, 2, 32, and that's it, okay? And then you can see how we move on to the 3s. We have 3, 3, 3, 13, 3, 23, 3, 33. Again, I'm pulling these out of the cross product of doing the cross product of set A to itself, okay? Crossing it to itself. These, out of all the elements that would show up in that Cartesian cross product, these would be the elements that would fulfill the relation of same ones digit as, okay? So, and you can see here, dot, 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 we could keep going all the way up to 10, right? Where the ones digit is 0, and we have 10 goes to 20, 10 goes to 30, 10 goes to 40, okay? And so on and so forth. Now we're going to say if we were able to exhaustively check all the elements in this relation, would we find all 3 properties? Well, let's see. The reflexive property means that each number reflects onto itself in set A. And we do. We saw that already. Okay, and I'm going to highlight those in yellow. We have 1, 1. We have 2, 2. We have 3, 3, right? Eventually, we'll have the same thing with 4, 4, 5, 5, 6, 6, 7, 7. They all reflect onto themselves. So, yes, it is definitely checking off the reflexive game. And here's some examples of them as we talked about, okay? Now, let's check if it's symmetric, okay? Remember, with symmetric, it means, okay, that you have, if you want to go back to the definition, what does symmetric mean? It means that you have A going to B and B going to A, okay? And if we look here at the examples, we would find that because you'd find that 1 goes to 11, right? But then when we were down to 11, 11 would go to 1. Okay? And 2 would go to 12, but so would 12 go to 2 when we're doing it at that point. Okay? So here's the examples of the ones that would be reflexive, meaning that you'd have A goes to B, and then later on in the Cartesian cross product, you'd have another element where they're flipped, and that would also still fulfill the parameter of the relationship. So it's definitely symmetric. Okay? And then when we look at transitive, transitive means that you have an A that goes to a B in the Cartesian cross product that belongs in the relation. And then you also have another element where you've got that B going to a different pair, C. And then you have that C being related back to A. And sure enough, that would happen here. Because you'd have 1 would go to 11, and here's the example they gave you. And remember that in this relation, it has the same ones digit, right? So as we're taking the cross product, we would find a pair of 1 and 11 because they have the same ones digit. And then we'd find the pair of 11 and 21 because they have the same ones digit. But we'd also have a pair of 1 to 21. And if we label those, this is A and this is B, right? Then you've got B going to C, and then here's A and C, fulfilling the requirement for transitive. So sure enough, this relation of same ones digit as from set A, which contains the numbers 1 through 40, fulfills the requirements for being reflexive and symmetric and transitive. So therefore, we can say that this is an equivalent relationship. Okay? Now, there are many equivalent relationships, and your textbook even gives you some examples. And I highlighted it here for you. Okay? There are ones that are common are if you do a relation of is equal to or is congruent to or is similar to, those almost always end up giving you what's called an equivalent relationship. In other words, those relationships will fulfill all of these three properties. Okay? Now let's talk about a definition of another term. There is a term here that we call a partition. Okay? Now, the definition for a partition is that it is a collection of non-empty pairwise. So it comes from having taken the Cartesian cross product of two sets. Okay, so but that relation has sets that are not empty. Okay, so they're non-empty. They're paired up, but they're disjointed subsets of set A, whose union is A. So in other words, when you take the union of these guys, they would go back to the original. Here is an example. Okay? If we have a relation called is the same one's digit, so the one that we just finished talking about, right? We would have partitions where you'd have all of the elements that pair up together that have 1 as 1 digits. That they would all be together. And then we'd have all the pairs that ended up with 2 as their 1's digits, and all the pairs that have 3 as their 1's digits, and 4 and 5 and so on, all the way until we get to 0, right? Each one of these is not empty. There is these little subsets existing wherein all those elements come together. But they're disjointed from each other, right? Meaning that they share no elements whatsoever between them. There are no elements in this little subset that are in this little subset, so they're disjointed. But if you were to take the union of them, and if you recall, the union is where you take all the elements of this one, and you take all the elements of that other one, and you put them all together to create this new set. If you were to put the union of these guys together, you'd get back the original set we started with, which was set A. Therefore, this is called a partition. This is a partition. 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 Okay? That is a partition for set A. Meaning, these are partitions that if you take the unions of them, it would give you back the original set we started with. Okay? So that's the definition of a partition. Okay? Now, a couple of things for you to note. Okay? Every equivalence relation of a set gives rise to a partition of that set. Meaning, if you find a relation of the original set A that fulfills all three properties, it's transitive, it's symmetric, okay, and it's reflexive, so therefore that relation is an equivalence relation, it will automatically give rise to these unique partitions. Okay, so equivalence relations have this sort of like default result, okay, or can't think of the word, sort of like collateral result. If you get an equivalence relation, the collateral result will be that you're going to end up with unique partitions of that set, okay? And the other thing you need to remember is that every partition that you find will be a set, and it will yield a corresponding equivalence relation, okay? So if you take every partition of that set, it will yield a corresponding equivalence relation. So what basically they're saying here is that they're sort of inextricably connected. If you've got an equivalence relation that you've created from set A, it's going to have unique partitions in it, partition sets, and each of those partition sets would give rise to a corresponding equivalence relation, okay? So they're sort of connected. And here's an example that they give you in the book that I have for the notes. If, for example, set A was these shapes, okay, and we wanted to create the relation same shape as, we would, if we took the Cartesian cross product of set A onto itself, and then we paired them up, we'd have all those pairs, but we use this relationship as is the same shape as, we'd end up with these partitions, okay, that you have here. And we'd end up with those partitions because this relation is the same shape as, would fulfill all the requirements of being reflexive, symmetric, and transitive. And you can see here the explanations as to why it is. Okay? So therefore, it would definitely be an equivalence relation. And if it's an equivalence relationship, then you know you have these unique partitions. And what they're basically telling you here in this note is, if you see that you have unique partitions, then you can say with confidence, oh, well, then that means that that was an equivalence relationship that this came from. Okay? And if you have an equivalence relationship, then you go like, oh, what's going to have these unique partitions? So basically telling you these two things always come together. So if you see one, you know you have the other. If you see the equivalence relation, then you know you have these partition sets that are going to happen inside of it. And if you see that you have these partitions happening, then you know, oh, it must come. That means that the relation we're talking about is equivalence. Even if you don't sit there and check to see if it meets all three properties, you would know that without having to check. If you then went and checked, you would see that it indeed did fulfill those requirements. Okay? So that's basically what they're telling you there. All right, guys, I'm going to stop my share here. All right? The homework that accompanies this lecture is found on page 385 and 386. You're going to do numbers 1 through 6. It's already posted under tasks, and it would be due by 1 p.m. on Monday. All right, guys, I'll see you later today for our live session, and hopefully I can answer some questions for you there. Have a wonderful day.